What if the reason we have never found extraterrestrial intelligence is not that alien civilizations are too far away, too quiet, or already extinct? What if the most advanced forms of intelligence no longer exist anywhere we would recognize as a place? Imagine a civilization so old, so technologically mature, that stars and planets have become as irrelevant to it as caves are to us. Then consider something even stranger. What if such a civilization discovered that space itself is not fundamental? What if distance, location, perhaps even time, are only emergent features of a deeper quantum reality, and intelligence eventually learned how to operate there? This is not something Leonard Susskind has claimed aliens actually do. There is no evidence that extraterrestrial beings live outside space-time, and modern physics does not provide a known method for escaping the universe into some higher realm. But ideas that Susskind helped develop force us to confront a possibility far stranger than ordinary science fiction. If space-time itself emerges from deeper quantum information, then our search for life may be based on assumptions about reality that are far more fragile than they appear. For most of human history, space seemed like the most obvious thing in existence. Objects had positions. Events happened at times. The universe was a stage, and matter performed on it. Even when Einstein transformed physics in the early 20th century, space and time did not disappear. They fused. Space-time became dynamic. Mass could curve it. Light could follow its geometry. Clocks could run at different rates depending on gravity and motion. The stage itself could bend. It was revolutionary, but space-time was still there. Then quantum mechanics arrived and made reality stranger. Particles could exist in superpositions. Entangled systems could share correlations across enormous distances. The act of describing nature began to require mathematical structures with no obvious resemblance to the world of tables, planets, or stars. For decades, general relativity and quantum mechanics remained spectacularly successful and deeply uncomfortable neighbors. General relativity described gravity as geometry. Quantum mechanics described nature in terms of probabilities, states, and information. The conflict became impossible to ignore around black holes. This is where Leonard Susskind enters the story in the 1970s. Stephen Hawking discovered that black holes are not completely black. Quantum effects cause them to emit thermal radiation and eventually, given enough time, evaporate. But Hawking's calculation appeared to produce a catastrophic consequence. Suppose you throw a book into a black hole, not because the book itself matters, but because the exact arrangement of atoms in that book represents information. According to ordinary quantum mechanics, the information describing a physical system should never simply vanish from existence. It can become scrambled beyond practical recovery, but the evolution of a closed quantum system preserves information. Hawking's original conclusion seemed to say something else. When the black hole evaporated, the outgoing radiation appeared thermal and featureless. The information that had fallen inside seemed to be gone, not hidden, destroyed. To physicists like Susskind, this was not a minor problem. If information could truly be erased, then one of the deepest principles of quantum mechanics might fail. A battle began. Hawking initially defended information loss. Susskind became one of the most determined opponents of the idea. The debate helped lead physics toward a radical new picture of black holes' gravity and ultimately space-time itself. One of the strangest clues had already appeared in the work of Jacob Bekenstein. Bekenstein realized that black holes possess entropy, a measure connected to the number of possible microscopic states a physical system can have. But black hole entropy behaved in a bizarre way. For ordinary objects, we expect the amount of information they can contain to scale roughly with volume. A larger box can hold more books, molecules, computers, or memories. A black hole seemed different. Its entropy was proportional not to the volume inside it, but to the area of its event horizon. That was astonishing. It was as though everything that could happen inside a three-dimensional region could somehow be encoded on its two-dimensional boundary. Gerard Hooft pushed the implication further. Leonard Susskind developed and championed the idea that became known as the holographic principle. A hologram is a two-dimensional surface containing information that can reconstruct a three-dimensional image. The holographic principle suggests something much deeper. Under the right description, all the physics inside a region of space may be represented by information on its boundary. This does not mean the universe is literally a holographic picture floating on a screen. It means dimensionality itself may be more subtle than it appears. And then, in 1997, Juan Maldacena discovered a mathematical relationship that changed theoretical physics. It became known as the AD-S-CFT correspondence. In simplified terms, Maldacena found that a theory involving gravity in a certain higher dimensional spacetime could be mathematically equivalent to a quantum theory without gravity living on its lower dimensional boundary. Two descriptions, different dimensions, same underlying physics. Imagine a world where everything you see, a planet, a falling stone, perhaps your own body, exists in a three-dimensional volume. Now imagine that the complete physical description of that world can also be written on a two-dimensional boundary surrounding it. Neither description needs to be fake. They can be two languages describing the same reality. This is where our ordinary concept of where begins to weaken. If two physically equivalent descriptions of reality can assign radically different meanings to space, then location may not be fundamental in the way our instincts insist. And the mystery goes deeper. Over the last several decades, work in quantum gravity has increasingly connected the geometry of spacetime with quantum entanglement. Entanglement is one of quantum mechanics' most disturbing features. Two quantum systems can become related so deeply that describing one independently of the other is impossible. Measure them, and their results display correlations stronger than classical physics can explain. Einstein famously disliked this kind of behavior. But experiments have repeatedly confirmed the predictions of quantum mechanics. Entanglement is real. The surprising question is what it has to do with space. A growing body of theoretical research suggests that patterns of quantum entanglement may help build, encode, or organize the geometry we perceive as spacetime. The idea is not that scientists have proven every inch of our universe is literally manufactured from entanglement. We do not yet possess a complete experimentally confirmed theory of quantum gravity, but in several powerful theoretical frameworks, the connection is unavoidable. Reduce certain patterns of entanglement, and the geometric connection between regions of space-time can weaken. Change the underlying quantum information, and the geometry can change with it. This suggests a breathtaking possibility. Perhaps space is not the container of quantum information. Perhaps space emerges from quantum information. Think of temperature. A single molecule does not truly have a temperature in the ordinary thermodynamic sense. Temperature becomes meaningful when vast numbers of particles behave collectively. The particles are fundamental to the description. Temperature emerges from them. Space-time may be something like that. At the deepest level, the universe may not begin with little objects sitting at locations. It may begin with quantum degrees of freedom and relationships between them. From those relationships, something resembling distance appears, then geometry, then space-time, then stars, then planets, then chemistry, then life. And eventually, on at least one small world, intelligence begins asking what reality is made of. Now imagine that intelligence survives, not for centuries, for 1,000,000 years, 10 million, 1,000,000,000. Human civilization has had electrical technology for only a tiny sliver of cosmic history. The first radio transmissions strong enough to leak significantly into space began barely more than a century ago. Our entire technological era is almost invisible when compared with the age of the universe. If intelligent life exists elsewhere, some civilizations could theoretically be far older than ours. And here we cross from physics into speculation. There is no evidence that any civilization has achieved control over quantum gravity. There is no evidence that advanced beings can detach themselves from spacetime. There is no known engineering blueprint for doing so. But suppose a civilization eventually understood the microscopic structure from which spacetime emerges. What would technology look like to beings capable of manipulating that structure directly? Our civilization manipulates matter. We rearrange atoms into buildings, processors, spacecraft, and machines. A more advanced civilization might manipulate fields with extraordinary precision. A still more advanced one might manipulate spacetime itself, something general relativity already tells us is physically meaningful, although our practical ability to engineer spacetime is essentially non-existent. But if spacetime is emergent, then there may be a deeper level still. Instead of bending geometry, perhaps technology could manipulate the quantum information from which geometry arises. And suddenly, familiar words become unreliable. Where would such a system be located? If its physical description existed in degrees of freedom that do not correspond straightforwardly to positions in our emergent space, asking for its coordinates might be like asking where the number 7 lives. The question itself could be malformed. This gives the search for extraterrestrial intelligence an unsettling twist. We usually imagine aliens living somewhere, a planet around another star, a moon beneath an icy crust, a megastructure orbiting a sun, a fleet crossing interstellar space. Even our most exotic alien stories usually preserve one assumption: intelligence occupies locations. But what if location is a primitive property only for primitive civilizations? Consider an ant moving across a sheet of paper. Its universe appears two-dimensional. It can move north, south, east, or west. Now imagine a human lifts the ant and places it somewhere else on the sheet. To the ant, the relocation could seem impossible. It never crossed the intermediate distance. But nothing supernatural happened. The human simply had access to a dimension the ant's ordinary movement did not include. This analogy is imperfect, and physics does not currently tell us that advanced beings can step into a literal extra dimension and bypass space. But it illustrates how deeply our intuitions depend on the structure available to us. The holographic principle is stranger than a hidden third direction beyond an ant's world. It suggests that two apparently different dimensional descriptions may encode the same physics. That means an extremely advanced intelligence might not think in terms of escaping space-time at all. It might instead discover that space-time was only one useful representation of something more fundamental. Something happened in black hole physics that makes this possibility even more provocative. Susskind helped develop the principle of black hole complementarity. From the viewpoint of a distant observer, information falling toward a black hole appears to become encoded and scrambled near the horizon. But from the viewpoint of someone falling with that information, there may be nothing locally dramatic at the horizon of a sufficiently large black hole. Two descriptions seem contradictory. Yet, black hole complementarity proposed that no single observer could access both descriptions in a way that would generate an observable contradiction. Reality, at least in quantum gravity, might resist being described from one universal classical viewpoint. Then came another extraordinary connection. In 2013, Juan Maldacena and Leonard Susskind proposed the idea often summarized as ER equals EPR. ER refers to Einstein-Rosen bridges, wormhole-like geometries. EPR refers to quantum entanglement after Einstein, Podolsky, and Rosen. The proposal suggested that certain forms of entanglement may be deeply related to wormhole geometry. This does not mean ordinary entangled particles provide science fiction tunnels for spaceships. It does not mean we can transmit messages faster than light. And it certainly does not establish that aliens are using wormholes. The idea is theoretical and remains part of ongoing efforts to understand quantum gravity. But conceptually, it is extraordinary. Two things that once looked completely different, geometry and entanglement, may be shadows of the same deeper structure. A bridge through space and a relationship in quantum information might not be separate ideas. They might be different expressions of one underlying reality. Now imagine trying to detect a civilization operating primarily at that deeper level. Our telescopes search for photons. Our radio arrays search for electromagnetic signals. We look for atmospheric chemicals, artificial lights, unusual infrared radiation, engineered structures, laser pulses, or technological anomalies. All of those are reasonable searches because they target phenomena that known physics allows us to detect. But they also assume that extraterrestrial technology leaves signatures in ordinary spacetime. An ancient civilization might not. Not because it is deliberately hiding, because its most important processes may no longer require the kinds of macroscopic structures we expect technological societies to build. Perhaps computation becomes vastly more efficient. Perhaps information storage migrates into physical systems unlike anything our instruments are designed to recognize. Perhaps communication relies on principles we understand mathematically but cannot yet engineer. Or perhaps none of this is possible, and every technological civilization remains permanently dependent on ordinary matter, energy, and causal signals moving through space-time. Physics has not answered that question, but the fact that we can ask it seriously tells us something about how dramatically our picture of reality has changed. There is another problem. Time itself may not be as fundamental as it feels. In everyday life, time seems absolute in one crucial psychological sense. The present feels real. The past is gone. The future has not happened. Relativity shattered the idea of a universal cosmic present. Observers moving differently can disagree about whether distant events occur simultaneously. There is no single master clock for the universe. Quantum gravity complicates the picture further. Some approaches suggest that time may be emergent or relational, arising from correlations between physical systems rather than existing as a fundamental external parameter. Again, this is not settled fact. The nature of time remains one of the deepest unresolved problems in physics. But if a future theory reveals that both space and time emerge from deeper quantum structure, the phrase outside spacetime takes on a different meaning. It would not necessarily mean outside the universe. It could mean closer to the universe's underlying description. Think about a video game. A character inside the game experiences a world of positions, directions, obstacles, and events. But that world depends on information processed by hardware that does not itself exist at a coordinate inside the game. The computer is not hiding behind a mountain in the simulated landscape. It belongs to a different descriptive level. We should be careful with this analogy. There is no scientific evidence that our universe is literally a computer simulation, and holography does not imply that a programmer exists outside reality. But the analogy captures one important possibility. An emergent world can be completely real to the structures inside it while depending on deeper variables that do not resemble the emergent world at all. Could intelligence someday move from one descriptive level to another? No known experiment says yes. No established theory says it is technologically possible. Yet intelligence itself is already a strange emergent phenomenon. The human brain contains roughly biological matter obeying physical laws. Somewhere within electrical activity, chemical signaling, memory, and computation emerges the subjective world of ideas. We discovered mathematics. We discovered atoms. We discovered curved space-time. We discovered quantum fields. We discovered entanglement. And now we are discovering hints that the arena in which all of these discoveries appear may itself be constructed from something deeper. If technological intelligence continues advancing, perhaps its ultimate trajectory is not outward, but downward, toward more fundamental layers of physical law. That possibility transforms the Fermi paradox. Enrico Fermi famously asked, in essence, if technologically advanced extraterrestrial civilization should be possible, where is everybody? The galaxy is old. Even slow interstellar expansion could, under many assumptions, spread a civilization across the Milky Way on timescales much shorter than the galaxy's age. Yet we see no confirmed extraterrestrial civilization. There are many possible explanations. Life may be extremely rare. Intelligence may be rare. Technological societies may destroy themselves. Interstellar travel may be too difficult or undesirable. Civilizations may choose not to expand. We may be searching badly, or we may simply not have looked long enough. But there is another possibility rarely considered outside theoretical speculation. Maybe advanced intelligence stops behaving like something that spreads visibly across space. Perhaps the most advanced civilization is not the one with the most planets. Perhaps it is the one that learns it no longer needs planets at all. Imagine two civilizations. The first colonizes 1,000 star systems, constructing enormous machines around suns. Its presence is astronomically obvious. The second learns to encode its civilization within extremely compact, stable, information-rich physical structures. It minimizes waste energy. It manipulates quantum states rather than moving gigantic masses. Eventually, if the deepest ideas of quantum gravity permit it, its activity becomes connected to physics at scales where our concept of spatial location loses meaning. Which civilization is more advanced, and which one would we notice? The first might light up the galaxy. The second might become almost invisible. There is something deeply unsettling about that possibility because it reverses one of our oldest assumptions. We imagine progress as expansion, more territory, more energy, more stars. But nature may reward something else, greater control over information. Susskind's work repeatedly returns to information as a fundamental organizing principle. Black holes seem to destroy it. Quantum mechanics insisted it should survive. Holography suggested that the information in a volume could be encoded on a boundary. Later developments connected entanglement to geometry. Piece by piece, information moved from being a bookkeeping device to occupying a central role in our attempts to understand space-time itself. So perhaps the deepest question about alien civilizations is not how far they can travel. It is how deeply they can understand information. Still, there is a danger here. Once physics becomes strange enough, it becomes easy to turn legitimate ideas into fantasy. Quantum mechanics does not mean anything imaginable is possible. Entanglement does not allow unrestricted faster-than-light communication. The holographic principle does not prove our universe is an illusion. ER equals EPR does not give us traversable wormhole highways across the galaxy. And nothing in Susskind's research proves that extraterrestrial civilizations have transcended spacetime. The scientific value of the idea lies somewhere else. It reminds us that when we search for intelligence, we may be projecting our current technological stage onto the entire future of intelligent life. A person living 10,000 years ago might have searched for powerful civilizations by looking for bigger campfires. They would never have imagined radio. Someone living 500 years ago might have searched the oceans for fleets and never imagined satellites. We search the stars for signals because signals are what we understand. But 1,000,000 years of scientific progress could change the very definition of technology. And perhaps the most extraordinary civilization in the universe would leave no fleet, no radio beacon, no glowing empire around distant stars. Perhaps its signature would be buried in subtleties of quantum physics we currently interpret as nature itself. That thought leads to a final, more disturbing possibility. Suppose space-time really is emergent. Suppose a deeper description exists. And suppose intelligence can eventually understand that description well enough to manipulate it. Would such beings still count as extraterrestrial? Extra means outside. Terrestrial means Earth. But those words assume separation by space. At a fundamental level, where ordinary distance no longer exists, the difference between here and there might not be basic. A civilization that originated 10 billion light-years away could, in the deeper language of quantum gravity, be related to our region of the universe in ways no classical map could represent. Not nearby, not far away. Those categories might simply fail. Perhaps that is why the deepest mysteries of extraterrestrial life and quantum gravity feel strangely connected. Both ask us to confront the limits of human intuition. We evolved to understand falling rocks, moving animals, changing seasons, and faces around a fire. We did not evolve to visualize Hilbert spaces, event horizons, quantum entanglement, or emergent geometry. Yet somehow the human mind has reached far enough to discover that the solid stage beneath reality may not be solid at all. And somewhere in the universe, if intelligence arose millions or billions of years before us, perhaps another mind reached that realization long ago. Maybe it built ships. Maybe it crossed stars. Maybe it transformed planets. And then, after centuries of searching outward, it discovered that the greatest frontier was not another galaxy. It was the structure beneath space itself. If that happened, we may continue staring into the sky, listening for whispers traveling across light years, never realizing that the most advanced intelligence in existence no longer needs to cross the distance between stars, because, perhaps, at the deepest level of reality, there was never any distance there to cross.